We've all heard the shift in pitch when a rapidly moving object goes by us. In 1842, Christian Doppler published an 11-page paper explaining how this happens. I'm going to try and explain the Doppler effect in 5 minutes with no equations. Why am I here with an acoustic bass guitar? To teach you about the Doppler effect. If I play a note B and move toward you at 44 miles an hour, you won't hear a B. Instead, you'll hear a note 1/2 step or 1 fret up. You'll hear a C. And after I pass you, you'll hear a B flat. So if I go by you at 44 miles an hour, that's what you'll hear. It doesn't matter what note I start on. You'll hear a note that goes a 1/2 step up to a 1/2 step down, whether it's a car or a bus or a guitar going by you. If I go by at 88 miles an hour, the difference is twice as much, a total of 4 1/2 steps. We need to understand how fast sound travels in air. This car is going 50 miles an hour. It takes it about 13 seconds to cover 1,000 feet, but through the magic of video, we'll do 2,000 feet at the speed of sound. Wow! That was fast, but not so fast you can't see it. Inside a car, we flash and beep at the same time. Outside the car, the sound is a 1/2 second late. Let's go into the lab and see how this works. From guitars to bicycles, I put a cable tie on my fork so it makes a click when the spokes go by when the wheel rolls. Let's go 1 revolution. "18 clicks, 6 feet between the tape marks." Hello! Let's imagine our bicycle is moving at 33 feet per second. If we roll it, we'll find in 33 feet it makes 100 clicks. So that would be 100 clicks per second. I can represent the distance the bike travels in 1 second by a line 1/3 of an inch long for 33 feet. Sound in 1 second goes about 1,100 feet, so I'll make a line 11 inches long. It'll come to our listener here. That's about 1,100 feet per second. The clicks are like little pieces of candy on a conveyor belt getting carried out from the bicycle towards the listener. And there will be 100 of them spread evenly between the bike and the listener if the bicycle is 1,100 feet away. Click, 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 click. Let's imagine that's the bicycle, and it's not moving, but the wheel's clicking, and these are the little dots of sound getting delivered to the penguin. They'll come by at a certain rate. But if the bicycle is moving when it's clicking, it's like this. Click, 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 click. And you'll see what happens is because the bicycle's moving towards the penguin, the green dots are kind of compressed. There's the same number as the red, but they're squeezed together and they're delivered to the penguin quicker. Here's the analog Doppler computer. A rubber band, little marks on it, 100 of them. You just set it down on a piece of paper that's marked off at 11 inches and stretch it out. And I have 1/3 inch marks here that represent the motion of the bicycle. Take a look at the right hand up close. If I want to see what happens when the bicycle's coming towards me, I just move the end of it in that 1/3 of an inch, and I count that 3 extra marks have come into the original 11-inch gap. So I'm going to get 103 clicks, 103 cycles per second. When the bike's moving away, I just stretch this out to here, and I say I've lost about 3 marks. 100 minus 3 is 97. I should hear a 103 hertz tone when the bike is coming toward me, a 97 hertz tone when the bike is leaving me. That's the difference between an A flat and a G, about 1/2 step. So let's get on the bike and see what happens. A flat down to G, 1/2 step. Well, worked out pretty well. That's what the video sounds like. So now we understand the Doppler shift a little bit. If an object's moving towards you, the sound waves that come from it are compressed or piled up. it's moving away from you, they're kind of stretched out. And that happens whether it's a hummingbird or a de Havilland Dash 8 airplane flying overhead at 3 miles altitude.